Good morning, this is Varshini, and I'm representing my team Joshnavi, Shirshika, and Geeta. NIM game. NIM is a two-player combinatorial game. This game consists of multiple heaps of tokens, and each player can take alternate turns. In each turn, one can choose any heap and remove one or more tokens from it. Goal is the player who removes the last token wins. Coming to the state-space representation of the NIM game, the state n is represented as an ordered tuple of non-negative integers, each showing the number of objects in a heap. The initial state S, it is the starting configuration given in this game. Operators or arcs. On each turn, chooses one heap and remove any number of objects from it. The goal state GD is that all heaps are empty. The player making the move into this state is the winner. The solution path is the sequence of valid moves from the initial state to the goal state. So this is a state space diagram of NIM game with the initial configuration as 1, 2, 1, and this path is one of the solution path for this game. Breadth First Search BFS. BFS explores all the game states level by level starting from the initial heap configuration. It systematically generates all the possible moves to find the winning or the losing states and the shortest winning paths. The implementation of BFS. We first enqueue the initial state, we dequeue a state and generate all the valid next moves, and then enqueue all the unseen states. And we repeat this process until the terminal state is reached. So this is the code for the BFS algorithm. We can see the output. The goal is reached here in three moves, and the solution path is this following four states. And in this BFS, the total number of nodes visited are 24. Coming to the best first search algorithm. The search strategy is we explore the nodes with the smallest heuristic value first. The heuristic value which we take here is called the nim sum, which is nothing but the XOR of the heap sizes. Nim sum is 0, means it is the losing state. States with smaller nim sum are considered better. The implementation steps for the best first search algorithm are we initialize a priority queue and insert the initial state with its nim sum. While the queue is not empty, we dequeue the state with the smallest nim sum and then generate all the valid next states. Then compute the nim sum for each new state and enqueue it if it is not visited. And we repeat this process until a winning or a terminal state is reached. So this is the code for the best first search algorithm. This is a function where we calculate the heuristic, that is the nim sum. Coming to the output of this code, we can see that the goal state is reached here by generating the number of nodes generated are 28 and the number of nodes visited are 8. Coming to the performance comparison of BFS versus BEFS. The search strategy in BFS is we explore the nodes level by level, whereas in BEFS, the nodes with the smallest heuristic value are explored first. In BFS, there is no heuristic, whereas in BEFS, the nim sum is the heuristic which we consider. The time complexity for BFS is order of B power D, and in BEFS is also B power D, but it's often faster in practice due to the heuristic. The space complexity of BFS is order of B to the power D, and BEFS is also order of B to the power D. But it's often smaller in practice as only the promising nodes are explored. And BFS always guarantees the shortest path, whereas in BFS, the shortest path is not always guaranteed. It depends on the heuristic which we consider. BFS is slow for large state spaces, whereas BEFS is faster in practice. And BFS explores all the possible moves, whereas BEFS it quickly finds the winning moves and uses the nim sum heuristic. The performance metrics of BFS and BEFS. Let us consider an example of an M game where the initial configuration is 1, 2, 3. In breadth first search, the number of nodes visited are 24, whereas in BEFS it is only 8. And the number of nodes generated in BFS is 24, whereas in best first search is 28. Coming to the conclusion, so BFS generally explores all the states level by level and it always guarantees the shortest path to the goal, but it has high memory and time usage. Whereas best first search with the NIMSM heuristic, it prioritizes the promising states using the NIMSM and it's faster in practice as it explores only fewer paths. Optimality depends on the heuristic, but it is efficient for finding the winning moves. So the key insight from this is combining heuristics with search strategies improve the efficiency without losing the correctness of the solution. Thank you.